My name is Nassir Cassamo. I'm here a wind energy scientist at TNO, and following an invitation by Eric, the idea today is we talk a little bit about the active wave control validation methodology that we have developed here at TNO. So this is a methodology that aims to quantify the gains from active wave control trials, and it aims to be used in a consistent and reliable way. And today here, within the context of this work package, I think it would be very interesting if we could discuss also some more details, especially regarding the uncertainty quantification. And so the idea that what I bring today forward is that we could go more or less through these points. So first, I would like to give a brief background and some context to how this methodology was first developed. And then I could give a brief overview of the different steps that are taken in the validation methodology, and also some examples based on a dummy data set. So the results that I show here today, what I mean by dummy data set is that we use only data from a wind farm where no active wave control is employed, so it's simply normal operation. But yet to give concrete and tangible evidence of how this methodology works, then we divide this normal operation of the SCADA into two data sets, simulating a normal operating data set and active wave control. And then I can go in a little bit deeper on the uncertainty quantification steps that are taken. And I think it's also interesting that we discuss a bit the sensitivity of the results to many different parameters involving uncertainty in the methodology. And then I'm also very curious to hear about your reflections, comments, so we can have also some room for a discussion regarding all of this. So this does not aim to be any type of academic lecture. So I'm very open that you just interrupt me if you have some questions or if everything is not clear. So please feel free to do that, or also wait until the end. That's also fine. Let me just start by giving a brief background of how this was initially developed. So the idea is that we can use a methodology in a reliable and consistent way to assess gains from active wave control in offshore wind farms. And this was initially developed within one of our projects. It was called Dynamic Robust Wind Farm Control, or in short, DISCON. We also explored other lines of research in this project, for example, robust wind farm control, and also assessing this type of controllers in dynamic simulations. I leave here a hyperlink if you are curious. There's more information there. It was also a project in collaboration with Siemens Gamesa. This was all initially developed by Dr. Stoyan Kanev. He made sure that everything was fully detailed and also made publicly available. So I also leave a link here so that you can access the report. And then, as it's currently now, it's maintained and it has been further developed also at TNO, especially to assess gains at the turbine level. So I also leave here a hyperlink to a more summary report, also focusing on this, also using dummy datasets. I also like to emphasize that when this was initially defined, there were also some requirements and goals that were defined. So for example, it should be applicable to large offshore wind farms of any layout, so no special requirements in terms of the layout of the farm. It should make use of the measurement equipment that's on site, so we shall not require any special MetMass deployment or LiDAR deployment. And so we also make only use, ideally, of SCADA data, 10-minute statistics or faster if necessary. So Stoyan has developed this methodology taking into consideration these initial requirements. All right. So let me now introduce briefly this validation methodology, and I try to segment this into 7 different steps. I do not wish to go into much detail on each one for the sake of time, but still provide a brief overview before I jump into the uncertainty quantification part. So going into these 7 different steps. So first, we just do an initial data rejection, meaning that we're going to remove curtailed turbines, not on-grid turbines, or even time instances where we do not use the same sensors consistently. So this is, of course, subjective to the user to decide on which measurement points he or she believes are of sufficient quality to assess accurate gains from farm flow control. Then the second step is that we do a calibration of the wind direction measurements. So if we use SCADA data, we are relying on the anemometry placed on the turbine that we know that has biases or offsets in the measurements. So we need to remove this offset from the wind turbine direction measurements. This is what we call the calibration procedure. And we do this by comparing the power ratio of turbines that's in the data with the power ratio of those same turbines using a wake model. We use our farm flow wake model, which is a Navier-Stokes parabolized equations to perform this. And if you have curiosity of this, you can check the report. Everything is fully detailed there with examples. And I believe that this method, it's also used in other tools. For example, we recently have the tool released by NREL Flask that also use engineering wake models to perform this kind of corrections through the power ratio. This method in our methodology, I think, goes a little bit one step forward, where it also does a quality check and to assess the convergence of this correction. And again, I invite you to read the report because everything is fully detailed there. And then when we have already our measurements corrected, we can estimate the so-called consensus or free stream characteristics. So we wish to compute for each 10-minute statistic a unique value of wind speed and wind direction of the incoming wind. And we do this by averaging local corrected measurements from each of the leading turbines. And we do this by identifying the leading turbines by using a wake model. We use the Jensen model, and we start by just averaging the wind direction over all the turbines, and then we identify the leading turbines. I'll give an example to make things more tangible in just 2 seconds. And then we can still do an additional filtering, which is really to ensure that we have the maximum quality of the data to assess gains. And this, for example, boils down into 2 steps. We can remove turbines that are downstream of curtailed or not on green turbines up until a certain threshold of rotor diameters. And we can also decide to maintain or to remove a certain time instance if we believe there is greater discrepancy between the local measurements of the leading turbines. So let me give you a concrete example here in this figure. So let us imagine now that we have pre-processed the data and corrected all of our measurements. And now we have here a certain 10-minute statistic with all of our turbines. So we have here in green the turbines that have been identified as the leading turbines. And we have here, for example, also an example of the local measurements corrected already. And also, in addition, we see here 2 types of turbines. For example, we see here in red a turbine that has been curtailed, and here in orange a turbine that has been not in grid connected to the grid. So the user can also decide to remove turbines downstream of this turbine by up until a certain distance of rotor diameters. And then in addition, we can also decide to maintain or reject this 10-minute statistic for our analysis by putting a maximum threshold in the standard deviation of the consensus wind speed and direction. So I think up until this point, everything is more or less straightforward. I think everybody that is more or less familiar with SCADA data analysis for whatever purpose it is, whether wake model benchmarking or whatever, is more or less familiar with these steps. So I think where things start to get interesting is from this point onward. So let me also spend some time here on the binning. So usually when we now have 2 data sets filtered, and then we have these 2 data sets for normal and active wake control operation. And it's interesting here, the binning that my colleagues coded, because we don't really divide just into bins. The way that this binning procedure works is that a bin will only be formed if the uncertainty within the bin is below a certain threshold. So let me show you here an example that we use from our dummy data set, which is also available in fully detailed in the report. So I have here a couple of bins. Here I have a wind direction, and here I have the uncertainty of each bin. And let's say that I first provide an iteration of how I wish the bins to be. So I say wind speed bins must be at 1 meter per second and wind direction bins at 2 degrees. So what happens is that you see here the colors represent the uncertainty over this first iteration of bins. But then the user will also define a maximum threshold and a desired threshold of how he or she wishes the uncertainty of this bin to be. And this is in black, represented in black and in red respectively. And then what's going to happen is that when you're going to have an iterative procedure where the sizes of the bins are going to change in order to meet these requirements up until a certain level of maximum width of the bin. So it's really an iterative procedure, like we're optimizing the sizes of the bins to meet certain requirements that we define. And up until this point, I've only said uncertainty, but it's of course important to say which value of uncertainty do we use. And in this methodology, the value that has been chosen is the normalized standard error of the farm power production. And in a little bit, I will also show how this value is calculated. And then the last two steps that can be done are the power ratio analysis. So we wish to then evaluate the ratio of the farm power production between active weight control operation and normal operation. And then we quantify this for each of the bins we have just calculated, and also the uncertainty in terms of 95% confidence intervals. And then we can also analyze these gains at, at the turbine level in terms of energy gains, but I'll not go into detail on that. But let's just see an example so you can see how this uncertainty is quantified around the power ratio. So here, for example, I have again data from my dummy data set. So everything is, I have here in red the mean power ratio between the two data sets for each of the bins I formed. So you see it's more or less 1 as should be expected because they're both normal operation. And also you see here in gray bars, you see the uncertainty quantification. This is quantified in terms of 95% confidence interval. So you see here 2 standard errors around the mean value. All right, so this covers more or less the initial part of the overview of the methodology. But the final value that we wish to assess, it's the AP uplift or the AP ratio over the whole test. And how this works is then that we have to account for the frequency distribution in the data, so the number of records that actually existed in the data. So then this is our last figure, is the AP ratio that we are interested in analyzing, and the corresponding 95% confidence interval. Now, also an important point I'd like to make is that this value will then be sensitive to all of the design choices that we have chosen so far for the filtering, and even for designing the binning procedure. So for example, let me show also here an example. So here I did a couple of tests. So I did 6 tests, and I put here some parameters that are fixed and are represented in gray. So for example, I decided that the maximum standard deviation of the wind speeds across the leading turbine should be 2.5 meters per second. The maximum standard deviation of the wind direction should be around 10 degrees, and the wind speed bin should be defined at each meter per second. I've also decided that I'm going to reject measurement turbines that are downstream of curtailed and not on grid turbines up until 25 rotor diameters. And then on my 3 first tests, I have decided that the maximum standard error per sector is going to be of 10% and the desired one of 5%. And on the last 3 tests, I just reduced this by a factor of 2. And on the first 3 tests, I'm going to increase the maximum sector width by 2 degrees up to 6 degrees, and then the same again. And you see that, first of all, the average bin size is, of course, going to vary. So I'm not always going to have the same bins exactly with the same size defined always to be the same across these different tests because of this iterative procedure. And that's always going to have an impact in my assessment of my AP ratio. So we see here that the values differ slightly, not a lot, but still slightly. They're very close to the expected value of 0 uplifts because this is our 2 normal operation sets. We see, for example, here we see 0.17%, but here we see already 0.92%. And we also see our accompanying 95% confidence interval, which can reach values, for example, of 0.3%. So the main key messages I have for you in this slide is that the final goal that we, in this methodology, is then to assess the AP ratio increase and the corresponding 95% confidence interval. But now I would like to deep dive a little bit on how exactly we quantify these uncertainties. And another core message I also have for this presentation is that in this methodology, we start by quantifying turbine statistics prior to calculating farm statistics, and then we propagate everything from turbine statistics to farm statistics. And I have here actually the mathematics because I think those are very interesting and I really like statistics. But for example, let me now deep dive into this. Okay, so first of all, the thing that we're going to define is the mean turbine power production for a certain wind speed bin and direction, so this B. And this is defined for every turbine T and for each of the two data sets S, normal and active wake control. So we're simply going to sum and calculate the average of the turbine power production values over this bin. So for each turbine, for each time instant that I have I. And I have a mean turbine power production. And I'm going to calculate also the accompanying uncertainties, or in this case, the variance of this turbine by simple statistical principles, and also then the accounting for the total number of points. I have the so-called variance of the mean value, or I believe this is just the squared value of the standard error. So far I have statistics at the turbine level following very basic statistical principles. Now I wish to propagate these onto the farm statistics. This is how then this is performed. We follow simple laws of propagation of uncertainties. And this works simply by calculating an average power production of the farm for my bin B, for also for the two data sets. And this works simply by summing the average mean power production from each turbine. And then what I think is very interesting is that how we quantify these uncertainties. So if we follow the laws of propagation of uncertainties, they dictate that we not only have to account for the variance of each of these turbines, but also the covariance of each of these turbines. So then we have to account for these covariance terms. And now this is also where we can have some different argumentation and interpretation. Because one may put the argument that we might consider differently covariance terms. So I may argue that if I consider all the covariance terms, then this is an extremely conservative approach, especially if I have a farm that I'm considering the covariance terms between turbines that are very, very distant. I might not want to consider this. I might want to have the power of having a spectrum of conservatism, which I wish to choose from. And so there's also the possibility of choosing which covariance terms to apply. And this is done, for example, here I have in this dummy data set the covariance matrix for all of the turbines for a certain bin. And if I just sum all these values, then I will have my total variance of the farm power production for this bin. But of course, now I can play around with this. I can design a so-called weight covariance matrix that allows me to choose which covariance terms I want to include. For example, let's say that I do not wish to include covariance terms of turbines that are very distant. For example, turbine 1, turbine 34. So I wish to disregard this covariance term. Then I can do this. Simply put here 0 and here 1, and then I calculate the so-called weighted covariance matrix. This is only to emphasize that it is also possible to have this freedom of how much conservative to be. So now, as we also have some sensitivity of results to the AEP ratio, then this is also going to influence the sensitivity of the uncertainty itself. And this is also a point that I would like to emphasize as a key message when it comes to quantifying uncertainties in this methodology. And especially regarding three key indicators. So the first that I would like to share with you, for example, is the bin width. The second is the bounds of the uncertainty itself, and the third is the AEP ratio. Starting with the bin width, I do something very similar that I have done before. So I have now also running 6 tests, and I maintain everything more or less similar. I've decided that the maximum sector width is going to be 6 degrees here, as you can see here. And I'm also going to say I'm going to vary the number of covariance terms that I include. As for considering covariance terms of turbines placed up until 5 rotor diameters, up until 30 rotor diameters. And of course, here what we see is that my bin width is going to increase as I include more covariance terms. Of course, this is to be expected, right? So we are being more conservative. And then if we wish to form more bins, we need to increase their size to reduce the uncertainty within them. So we have more data points. And so we see, of course, there is my main message is there is some sensitivity also to the average bin size in terms of how conservative we are in considering these covariance terms. When it comes to the uncertainty bounds, we also see some sensitivity, of course, and this should also to be expected. Here, for example, I have uncertainty bounds of 0.053% if I only include covariance terms of turbines placed within 5 rotor diameters, if I start being more conservative, then of course I see that my confidence interval of my AP ratio is going to increase. But I think it's interesting also to quantify by how much this increases. And we see here in this dummy data set example that it increased by a factor of 4. And then, of course, the AP ratio itself is also going to have some sensitivity because we are changing also the sizes of the bins that we choose, the bins itself that we choose. And of course, here in this dummy dataset example, if I just use 5 rotor diameters, I have an uplift estimated of 0.18%. If I started to be more conservative, I fall within the 0.0% range, which is more or less expected for this dataset, right? We should expect to see 0% uplift. Of course, there's always some uncertainty surrounding this value, but I think it is interesting. And I suspect that this is the case because as we are being more conservative or including more covariance terms, we also have larger bins, so it is perhaps possible that we just homogenize our final solution. All right, so I just wanted to share some key highlights that I think are key takeaways from this. So first of all, we have developed this methodology. At least my colleague Stoyan has very well developed this initially. And it is a methodology that aims at quantifying the benefits of using active wave control in offshore wind farms. It only makes use of instruments already available in wind farms, so we should not make use of any other LiDARs, and it only makes use of SCADA data, 10-minute statistics, or faster if necessary. It also has very dedicated techniques that allow us to increase the quality of this assessment, for example, removing offset or biases from the measurements through this direct calibration procedure that you can read more in this report by my colleague, or also optimizing the wind direction bins by considering the uncertainty and other criteria. I think also this approach follows the so-called frequentist approach in statistics, where we are calculating our uncertainties considering the standard error, which considers the number of points. I believe that there are also other techniques, for example, more Bayesian techniques involving bootstrapping, and I'm trying to here discern between the so-called frequentist approach and the so-called Bayesian approach. They're often referred as two different approaches in statistics. I think this approach follows more the school of thoughts of the frequentist approach. And the final outcome is always to evaluate the calculation of the AEP uplift, or how is it referred to in this methodology, the AEP ratio, and the corresponding 95% confidence interval that is propagated from turbine statistics. And the results themselves are, of course, sensitive to the defined criteria. We also see that the quantification of uncertainty itself may also be influenced by the amount of covariance terms that exists. And the core message here is that it's really up to the user to decide how to be less or more conservative and make a decision of how he wishes to evaluate. And then all in this presentation, I only had enough time to cover the so-called stochastic part of the uncertainty that's really based on the measurement data. But in this report, you also have a lot of more information or a lot of detail on how one could quantify also deterministic uncertainties. And deterministic uncertainties refer to the so-called two categories of category A and category B of uncertainties. So in the report, you can also find more information on that. And I also would like to finish with some thoughts, some comments, reflections, and also open up the room for some discussions, which of course some thoughts that I have on my own. Now, also be interesting to learn from you what other approaches would you suggest to quantify uncertainties. For example, if we look at the recently released tool from NREL Flask, a lot of bootstrapping is used. And this is used, for example, to quantify uncertainties in the energy ratio. And my question is, are these methods really comparable to the frequentist approach? I really don't have an answer for this. Do both consider the number of points in each bin in the same way? And what will be the implications of using these two different approaches in statistics, more classical and more Bayesian approaches, I would call them. We also see that the results can be sensitive to the options used in the examples, And I also like to ask you, so do you believe that experts and also the purpose of this IEA task should be to decide or agree on certain rules of thumb, or will always that be left to the users of these methodologies that have the responsibility of assessing this? And also, what other developments would be of interest to support ongoing campaigns? We have now the Awaken campaign in the States. We also see that sometimes other ratios or metrics or KPIs are used sometimes, the energy ratio as opposed to the power ratio. So is there really an agreement of what metric is most suited to analyze the gains? So I also leave some questions of my own that I think are interesting for discussion. So I hope this has been of interest to you. It's something that is of work also, and I think also some research gaps that have been tried to fill in with this kind of work. So thank you very much for your attention, and I'll be here to answer your questions.
Great, thanks so much, Nassir, for that interesting presentation. I see we have a couple of questions from the audience. So Matthias, I think you raised your hand first.
Yeah, interesting stuff. I think I've seen some of this work in the past. I've seen this, I think, a paper, a white paper, something similar on this in the past. And we have tried similar things. And what we have found is that the methodology itself is not what drives the uncertainties. It's equally how you define the test. So what I'm curious about is the data set you have here. How have you basically, I guess you painted on a fake on and off signal in the testing set or something similar to that. Could you elaborate a bit more about that?
Yeah, in this case, we just take SCADA data and we just divide it. So from normal operation, and just divide it into two data sets. One that simulates as if it was in normal operation and the other in active weight control operation. And then we simply take the ratio and evaluate the gains from that. So there should be no gains, of course, but it's as you have said, just one simulating that it was toggled with the on operation.
Have you tried? Then I'm curious, what kind of toggling speed, and do you throw away data or anything like that?
Yes, actually, yes. I think that's also defined in the methodology, if I'm not mistaken. But some periods after the toggling has been put are suggested to be removed. Yeah, I think that you also find that in the report, a suggestion of the time instant to removed after the toggling period.
Yeah, we did an investigation of almost 2,000 offshore turbines where we tried, let's say, simulating this and then simulating various quantification methods. Yeah, a while back, and one of the methods were very similar to what you've done here. But what we found is that sometimes, if you are unlucky, your swap pattern, or what you want to call your swap time, goes in phase with some of the, let's say, performance fluctuations you have across the site due to other environmental parameters, of course, the ones that you are binning from here. So if you're unlucky, you would get, you have a bias term here that you expect to be 0. In this case, I believe it was around 0.1 or something. And we tried then bootstrapping over starting times. So instead of starting Monday at 12, we started at Tuesday at 9 or Tuesday at 1 or whatever, and then bootstrapped, I don't know, 1,000 times at random start times. And then we did that also for random swap times. So basically you imagine a matrix of swap times versus, well, ultimately you collapse it into, you get a distribution for each swap time. And there we saw it didn't really matter much with the methods we applied on top of the test, or the simulated test. The major driver in uncertainty was this swap time. And of course, some of the obvious ones are, if it goes into the diurnal cycle, which is quite obvious. So if you swap every day at noon, you get weird results. But we also got other examples, and then we did basically a qualitative analysis, try to find out what happened. So we can see that we had some temporal patterns. So basically imagine making an FFT of your power signal or some performance metric over the year. And if that coincided with your swap time, then we got, well, all hell broke loose. So we definitely found there were some learnings that slow swap times was not the way to go. And sometimes you're just unlucky because it's very difficult to design ahead of time when you have the test. You're not, you go ahead with the test and then you find out afterwards if you're lucky or unlucky.
Yeah, I think I understand your comments. I think I have also 2 comments on that. So I think my colleague Stoyan also did an analysis on the ideal swap time that would reduce the uncertainty. I think that's also in the report. I think similar to what you have here stated, but perhaps with another methodology. But there was also a study done to try to find the best swap time to reduce the uncertainty in the campaign itself. So I think there was also kind of an optima or a value that would reduce the uncertainty to avoid these biases from the urinal times, cycle times. But even when I guess the main, then the core of this presentation also then is not really the focus of the uncertainty on the campaign itself, but also on the data retrieved from the campaign and in analyzing it. So I guess at the end of the day, when campaigns are performed, right, we always need a methodology. And I guess we just have to live with the uncertainty that exists inherently in the swap time or in this swap test due to the swap time. I'm not sure if you agree on how you see that, but how then did you make a decision about the swap time? You just have to live with those uncertainties, right? Or do you see it differently?
Yeah, we did something similar in your first couple of steps, basically cleaning the data, make sure it's coherent and removing outliers and whatnot. And then we processed a lot of data, and then I can't remember the swap times. It depended on where we were in the world, but and also the scale of the farm, because some farms, you have to consider if they're massive, then this propagation delay, you have to throw away a lot of data if you swap quite rapidly. So I would say that the swap time would be depending on the layout and where you are in the world, but it's, I think the numbers we got were 70 minutes to 130 minutes, something in that ballpark, seemed to be quite good for offshore, for the scale of most of the farms we looked at. And then we had some of the bigger clusters. So I think we had 50 kilometers from the most extreme turbines. So some fairly large clusters.
Okay, interesting. Thanks for sharing that.
And if we got the swap time right, I think I got more or less the same uncertainty levels as you posted there, roughly speaking, within 50% of what you have.
Okay,
and then
interesting.
Normally unbiased when we got to the lower swap time. There are some places in the world where, we had some unexplained biases, but other than that, yeah.
Okay. Well, thank you for sharing that, Matthias. I think it was very interesting.
No, I think this is also very interesting what you've done here, and the first steps you had there were non-trivial. So I look forward to seeing some of the links you've sent.
Great. So Dan, you had a question as well?
Yeah, hi. It was a really interesting presentation. I think we don't often see enough of these important details in publications, so it's good to see more. I'll try to answer one of your questions, and then I'll ask my own question. So I'm not an expert statistician or anything, but regarding the question about bootstrapping, my understanding is that the big advantage of bootstrapping is that there's no assumed distribution, whereas the frequentist approach kind of has the underlying assumption of a Gaussian distribution. So if you can look at your distributions, then you can pretty quickly tell yourself whether or not bootstrapping would be an improvement. So that's the main thing I know about it.
Okay.
My question, I'm wondering, I know you only have this one sort of dummy data set, but if it's at all representative, I'm really curious. And maybe you showed this, I missed it, but how much data did you throw out? And really what I want to know is, like, if this were a real campaign, how long did you have to record for? Like, how many days of data did you need to get the useful set that you actually used?
That's an interesting question. So I think also in this report that I put in the link, you will see that this was designed for maximum campaigns of 1 year. So I think that's what is suggested in the methodology itself when it's reported upon. In terms of the data that's rejected, that's going to vary depending on the filtering criteria that you use and how conservative you are. I don't know the values by heart, but I know that they are in the report saying how much data has been rejected. And I would also argue that that will also be dependent on the wind farm and the location of the wind farm that you have, right? You might see some turbines that are more curtailed by the grid operator than others. So I guess that will also be sensitive to the wind farm itself. But I believe that all these are in the report, especially for these two examples that we do in the dummy data. So data from Anholt and Westermolstorff was used. And I believe that in the report, there are the two percentage of data that was rejected from that specific analysis. It will always be varying also between the filtering criteria that you use and how conservative you are at the end of the day.
Right. Okay. Thank you.
I think you had a similar question, Carlo. Was it answered there? Or do you have any other questions?
No, I think he answered. Yeah, the question was how long is the data set? It was shown in the presentation. I understand 1 year, is that right?
So this data set, I believe it was for 2 years, but I also think that the question that we received was how long should a campaign be? And the answer to that question would be this methodology was designed, I believe, to take into account campaigns of 1 year. But in this dummy data set, and I think these in 2 data sets that we use in our tests, it was data sets of around 2 years.
Great. Mike, do you have a question?
Yeah, thanks for the presentation. Could you go back to, oh, sorry, you're not sharing your screen anymore, but you had a nice flow chart which was describing the steps in your process.
Yeah, I can share it again.
Great. Yeah, I was curious and trying to make sure I understand what you were presenting, that at some point you had a quality filter which checked the performance of turbines which are operating in the free stream to make sure that they're within similar performance. Is that a part of this? Yeah, so we would reject time instances where the standard deviation of the consensus wind speed and wind direction do not comply with a certain threshold that the user defines. So I understand how you would do that for standard operation where all of the turbines are operating in the same fashion, but how would you do this during part of the experiment where different turbines are operating in different control strategies? So I imagine that even if you have an active weight control campaign with some yaw misalignments, I mean, you always have to make sure that the wind speed and nacelle transfer functions are accurate, that you can reproduce an accurate mapping for the wind speed upstream, and that even that you have a campaign, then you can rely on the anemometer of the turbine after making sure that the nacelle transfer functions are properly performed, and also after you perform the calibration for the offsets, and you use the calibration of the offsets from the nominal data set, and then you apply them also to your active weight control test data set. And you can also perform this estimation of consensus speed by using local measurements. This is what the methodology proposes. Does that make sense? Yep, makes sense. Yeah, so you basically use the pre-calibration of the nacelle transfer function within that. Yeah, understood. Yeah. Thanks. And I think also the report, if you're curious, goes a bit in more detail in that of how to check for the wind speed nacelle transfer function. It's not something I go into detail in this presentation, but everything is fully detailed there.
All right, so excuse me, I do want to leave some time to talk about the best practice paper ideas. So maybe we'll just take the last question now. And if there are any more questions, you can reach out to Nassir afterwards. So David, you have your hand raised.
Yeah, I haven't been able to think that through, but I have a question. Is that methodology, does that also work if you have another wind farm next to yours, and depending on the wind direction, your wind farm is waked by the other one, and obviously your free stream turbines are not really free stream turbines, but they are your front row turbines on one side of the farm, but on another one they are real free wind speed turbines.
Hi, David. Thanks for the question. Yeah, I think that's a good question. Well, we would have to test that on a test data set to actually assess what's happening there. I don't have a test data set where we have like clusters of farms, but it would be interesting to test and see how the uncertainty play out, and how then we would go about defining what is actually a consensus wind speed mean direction. But that's a very interesting question, and we're actually also discussing this question internally. And if you want to have a more thorough discussion on that, you can always reach out to me or my colleague Feike, because that's something also that we're discussing internally now. That's a good question. Yeah.
And maybe the other question, I think we chatted about this actually some time ago, and I had never had really time to read the report in detail. But my question, the other question is about the long-term correction of the result. That's always something when you have usually your windrows is maybe from historical times of let's say free stream measurements, and then you have new wind farms built around, and all of a sudden you have more like a wake affected windrows. And you know how that factors into your AP assessments when you talk about long-term gains, not just from there. So those things I think are important once it goes into the, I would say, more commercial assessment of the benefit rather than just the energy estimate. So yeah.
Yeah, that's also a very relevant remark. In the methodology itself, we don't go into much detail on how to perform long-term corrections. We can either use also long-term historical roses to have this the weights of the bins, but we also use usually the data that is filtered within the campaign itself or the test data set. So I have no assessment of how these two figures would compare if we would try to replace the weights in the data set by a certain frequency distribution and see how the two would compare. I have no insight on that, but I do believe it's a relevant point, and I do agree that it's especially relevant for commercial applications.
And I'm not sure whether a dummy data set actually would show that impact, or whether you have to have a real example where things change also with neighboring wind farms around, so that you then see the way you do the long-term correction changes your end result. And I don't know, maybe on a dummy data set with no upside, you may not see that impact, but I'm not 100% sure.
Yeah, perhaps it's true, but that is really state of the art. That's really tackling the really research gaps. Yeah, we'll also be curious to do it in the future. But thanks for the question.
All right. Well, thanks again, Nassir, for the presentation, and thanks everyone for the good questions. I will definitely interested in looking at the report for more details. And yeah, I also I thought you had a good comment about comparing the uncertainty resulting from the frequentist approach and bootstrapping, especially since most publications seem to use bootstrapping. So maybe that's something we can do with the example NG dataset.